Hello, everybody. Thank you for joining us today for our weekly Urban Water Innovation Systems webinar. We are wrapping up the Thrust B series this afternoon and are excited to learn more about urban water demand forecasting with a presentation from Dr. Sybil Sharvelle at Colorado State University. Thrust B focuses on innovative technological solutions using the data, models, and enhanced process understanding developed in Thrust A. As we've learned in previous webinars, a variety of solutions are explored under Thrust B, including resource recovery and reuse systems, green infrastructure, sustainable urban drainage networks, and resilient floodplains. This webinar will be recorded and posted to our YouTube channel. As always, a link to the video will be distributed as soon as it's available. A quick reminder that you have all entered muted, so please enter your questions into the chat queue and we will address them at the end of the presentation. We are still coordinating schedules for the Thrust C and D webinars, but once those are finalized, the schedule will be announced and posted on the calendar, which is available on the UN website. And with that, I'm excited to introduce today's speaker, Dr. Sybil Sharvelle, Associate Professor in the Civil and Environmental Engineering Department at Colorado State University, where she also directs the Urban Water Center. Her doctoral work included development of a system for treatment of gray water for potable reuse during space missions. This project led to her current interest in sustainable water systems, in which she has led projects funded by the Water Environment Research Foundation, US EPA, and Water Reuse Foundation. Dr. Sharvelle was a member of the National Research Council Committee for Beneficial Use of Gray Water and Stormwater, and chaired the NWRI panel for Decentralized Non-Potable Water Systems. And with that, I'm going to hand the controls over to Sybil, so bear with us for just 1 second while we transition here.
Excellent. Thank you, Sarah. Thank you, everyone, for attending today. So today I'll be talking about some results we have from our integrated urban water model and focusing on some of the impacts that can happen from urban growth and development as well as climate change in terms of water demand. Oh, I got it. Okay, sorry for that. Just needed to switch my settings a little bit. Okay, so most of you that are part of the UN project have heard a little bit about our integrated urban water model. Perhaps for some that haven't, that are joining today, I'm going to go ahead and review a little bit about what that does. So the purpose of the integrated urban water model, or IUWM as I'll refer to it, is to forecast urban water demand and project potential savings from conservation and water reuse strategies under varying climatic and land use conditions, including population growth. So what this model does is take nationally available data from databases and makes use of that to project urban water demand, but it enables overlaying of that with different scenarios of water conservation and reuse to ultimately be able to provide forecasts of water demand in urban areas. So the demand reduction strategies that IUWM can model include indoor and outdoor water conservation. So that could be installation of conservation fixtures inside the home, like a high efficiency laundry machine or low flow toilets. It also can include outdoor conservation strategies like efficient irrigation systems or the systems that could perhaps detect rainfall events and respond to those. So there's the potential to model all of those different strategies for water conservation. But in addition, IUWM is also able to look at use of several different water sources, including gray water, stormwater, and wastewater effluent. So these strategies are of interest to a lot of communities across the United States, and there's different drivers for those. For example, here in the western United States, where conditions are more arid, we may consider installation of a stormwater harvesting system for beneficial use due to the arid conditions and to meet our water demands. However, in the eastern United States, where people are on combined sewers, a lot of those projects are coming up to reduce combined sewer overflows. So there's there's a lot of drivers and there's a lot of differences in geographies and how that can impact these strategies. And many cities across the United States are interested in these different strategies, but a lot of questions remain, like how much demand can we really reduce by implementing these strategies? And then which strategies should we really be promoting in a particular area? What are the most effective strategies based on climate and other local conditions? And then what strategies are going to be most reliable under future pressures, particularly climate change? So really, the integrated urban water model was developed to address all of those different questions. It's a mass balance-based model. So it models the urban water system from a mass balance perspective. And this diagram shows the entire mass balance that the model works from. So at the top, we see water supply, and there could be either raw water or precipitation. You can see arrows coming in there because other potential sources of supplies can enter into the system, like wastewater, gray water, those different kinds of wastewater. And so the sources then become treated raw water, treated gray water, and treated wastewater. And then we have stormwater that results from precipitation events. So those are kind of all of our sources. Then in the yellow box are all of the demands that could be expected in an urban area, and those include both residential demands as well as what we call CII, which is on the far right here, which is commercial, industrial, and institutional demands. Those residential demands are separated by potable and non-potable demands. So the potable demands include bath, laundry, shower, faucet. There's some water that we always lose to leaks, dishwater, and then the non-potable are toilet and irrigation. So IUWM actually enables use of any of these various source waters, being gray water, wastewater, raw water, or stormwater, to meet either potable or non-potable demands. From a pragmatic perspective at this time, we're kind of still pretty far away, really, from being able to make use of some of these source waters as a potable source, like gray water, storm water. However, that's a possibility in the future, and so IUWM does have the capacity to evaluate what the potential are of those different source water end-use combinations. And then for each of these various fixtures we have in the system, we can generate either gray water or wastewater or both. So the gray water fixtures include your bath, laundry, and shower water, whereas the black water sources include toilet water and any kitchen water. And then we have our commercial, industrial, and institutional, which is a pretty variable water usage within the city and really kind of has to be set specific for a particular urban setting. So down at the bottom then, we produce gray water and wastewater, and those both have the potential to either be treated and reused or discharged into the system, and that's where we get the losses. Okay, so the way that IUWM works to project water demand is that, like I said earlier, it makes use of these nationally available databases. So it collects based on a GIS interface. Once a user selects an area, then the tool works through ERAMs and works to collect data on climate, land use data, and then population and household data. So the default databases for those are, for climate, we use the NAR database, and then for land use, it's NLCD, or the National Land Cover Database, and then we use census data. So after the user selects an area, then the model goes out and fetches all of that data and enters it into the model, essentially, and can do that based on these various blocks. So the picture you see here is the city of Fort Collins separated by block groups. And based on all of that data, then IUWM can characterize an area in terms of these various parameters you see in the third box to the right. So looking at precipitation, solar radiation, and temperature in terms of climate data. And then from land use data, we're able to estimate pervious and impervious area. And then from the census data, we can estimate population and households. And that population and household data can be used to estimate indoor water demands. And the projection of stormwater happens from percent of impervious area combined with your climate data. And then irrigation demand is based on a percent of pervious area combined with the climate data. And I'll go into more details about how the integrated urban water model actually estimates these various demands. However, the kind of take-home message from this particular slide is that these national databases are used, and then IUWM is able to make a pretty quick projection of indoor and outdoor water demands based on that selected area and some default parameters that are in the model. Okay, so this is what the interface looks like in case you've never been familiarized with IUWM. Basically, like I just said, a user would select an area, and that can be from they can draw a polygon or a rectangle. They can upload a boundary. So oftentimes when I've worked with IUWM, I upload a service area boundary, so a GIS layer that has information for the water service area for which I'm interested in. There's also some known boundaries like counties and cities and things like that. Then the user can select where they'd like to get all of the data that would be used. I just talked about that a lot. So it can make use of these nationally available databases like are selected here, or a user, if they have a better available data set, can upload those data for climate, land use type, and population. Okay, so to estimate indoor demand, like I said, the model does make use of the number of households and population in a particular area. Then we also make use of some of the studies that have been conducted, particularly by the Water Research Foundation and American Water Works Association. So there have been these various residential end use studies, or REUS. There was one published in 1999 that provides a good estimate of houses that are constructed before the year 1999. Since then, a new study was just published in 2016 that characterized, again, water use throughout the United States in many different homes in different cities, and did find a lower usage of water in households. So we've started, so the RUS 1999 found 177 gallons per household per day usage, whereas in 2016, the study found approximately 138 gallons per household per day. So our household water usage for indoor use has gone down pretty substantially since 1999, and that's been a common trend throughout the United States. There also have been some studies on most efficient homes for water use, or high efficiency homes, where they can get down to about 112 gallons per household per day. So that kind of represents where we are now in terms of what people can achieve as a kind of a maximum for water conservation in the home based on current technology for appliances, as well as really social acceptability in terms of what people might be willing to adopt for those particular fixtures. So that study was done in 2011, but a user can then select kind of a mixture of homes in their area, and then if they want to run through scenarios, they could look at, for example, 100% of the area being the high efficiency homes that achieve the 112 gallons per household per day. So this provides some more information on these various studies. So remember, we had the 1999 study, the 2016, and then the high efficiency new homes, or HENH. And again, these household water usages in gallons per day are indicated here. And really, in most cities that we look at, if you're characterizing the entire municipal area, the IUWM 2016 typically provides a really good estimate of indoor water use at this time, so about 138 gallons per household per day. But since we, in our model, often look at things from a block group or even smaller level of analysis, then we have the need to fine-tune things to really understand how much of the high efficiency may have been adopted. And in an area where you have a lot of older homes, if those haven't been retrofitted, then you may use values more toward the 178 gallons per household per day. These alpha and beta coefficients are simply coefficients that feed into the projection of water demand based on typical number of people in the home and number of households. So those aren't too important, but you can see how those do vary across the different household types and water usages that we've had historically. And I'll revisit those, so that's the primary reason for providing those values. Okay, so we also estimate outdoor demand using IUWM, and here we really use a combination of parameters that represent the physical system, as well as parameters that represent people's behaviors. So if we just kind of look at this equation, this QIT is your irrigation depth at each time step, and IUWM works at a daily time step. And so you start by looking at the fraction of evapotranspiration that's met, and then using a plant factor and the potential evapotranspiration that we estimate based on the weather data that we use for the model. So we first have all of those parameters, and then you subtract from that the fraction of precipitation to which irrigators respond. So that's a KIPCP parameter. And basically what that does is also represent behavior. So you can represent if people respond to 100% of the irrigation, 100% of the precipitation that occurs, then that would be a value of 1 there. So you would be subtracting out the depth of precipitation. However, that's not typical. Many homeowners have, and commercial water users, have automatic sprinkler systems that turn on and irrigate whether there's been a precipitation event or not. So we can then account for what percentage of the precipitation that people do account for. So there's typically some response from precipitation events. And then our parameter on the bottom here is just the irrigation application efficiency. So that would represent the type of irrigation systems that are used and how efficient that those are. So you can see, like I said, we have parameters that represent the physical system, like the depth of precipitation and the evapotranspiration that occur in a particular area based on the weather data. But then we also have other parameters that represent how people behave in terms of the fraction of evapotranspiration met and the efficiency of an irrigation system in response to precipitation events. So one of the major functions of IUWM is also to be able to project water demand under different scenarios of climate change as well as land use changes. So on the left over here shows the interface and how you can run different scenarios of climate. So there's kind of 2 choices here for the climate. One is that you could upload a climate file that has future projections of climate and different scenarios of those. The other could be to run a scenario with a temperature offset or precipitation scaling so that you're changing from the historical water weather data set, you're changing by a certain percentage, either temperature or precipitation. So you could look at warming conditions or cooling conditions, as well as looking at different changes in precipitation, increases or decreases that could impact water demand. So there also are the land use scenarios on the right side, and that enables looking at different scenarios of population growth or decrease, for that matter. So you can look at how population changes over a given time period. And with that, you would likely have a relative change in number of households that are occupied. And then you have all of the different development area types: open space, low density, medium density, and high density. And we can represent a change of those various given development types. So you could, for example, run scenarios where you look at conversion of open space into medium density area, or you could look at medium density, changing that into a high density development. So there's lots of different scenarios that you can look at in terms of land use type. Okay, so now I'm going to move along. Now that we understand really how the model works, I'm going to move along to a demonstration of the model in the city of Fort Collins to both look at strategies of water conservation and reuse, as well as different scenarios of climate change and development change. Okay, so this is just some general information about the water service area that we modeled. It was about 52 kilometers with a population of 97,000, and that was for that included about 40,810 households. The area is 50% low density area and 23% open space, 21% medium density, and then very low high density development. So just 6% of the area is high density. So, most of you have been to the city of Fort Collins and know that it's primarily a low density development city. And that's kind of important as we look at our results moving forward. Okay, so this shows a graph of the verification of the integrated urban water model. So we calibrated the integrated urban water model to historical water use in the city of Fort Collins. This shows data from the years 2013 and 2014. And even though the model works on a daily time step, I'm showing here monthly data. And that's kind of interesting here because we can look at particularly the trends in outdoor demand. So let me start by just explaining kind of the color coding here. So we have two shades of blue, both representing residential indoor demand, and then two shades of green representing outdoor demand, and then the grays represent the commercial, industrial, and institutional, or CII demand. So what we see here is the darker side also represents the observed data that we were able to get from the city of Fort Collins, and then the lighter shades show the IUWM projections. So you can see pretty close match between the observed and simulated results. And the nice thing here is that we also see a good representation of kind of how that irrigation demand increases through the months of April, May, June, July, August, and into September, and then decreases again in October. The model does a pretty good job of estimating those outdoor demands with the seasonal changes. Okay, so this now shows some statistics from the calibration period. So we have one calibration that happened from 2000 to 2009, and then a different from 2010 to 2014. And if we look at, we have the Nash-Sutcliffe statistic, the mean residual air, and bias. We see that we get pretty good estimates. We do a lot better in general with residential indoor demand than we do with outdoor demand, which is to be expected. It's very difficult to estimate all of what can happen in terms of outdoor demand with respect to people's behaviors with their irrigation systems, how they respond to precipitation events, and all of those kinds of things. So, however, like I showed in the previous graph, we had pretty good match with the data. One thing to know, here's the one question I get sometimes: why is there not a Nash-Sutcliffe for the indoor residential demand or the CII indoor demand? And that's a hydrologic statistic, and really kind of relates to variability, how the model captures variability. And since there's not month-to-month or even day-to-day variations in indoor water use, it's pretty constant throughout the year as well as on a daily basis. That statistic just doesn't represent the data very well. So if we move over to the far right of this table then, we did a testing using the calibration data from the years 2000 to 2009 and tested that on water use data from 2010 to 2014. And there we see actually a pretty poor fit in terms of the model's projections with the actual observed water use data. And the reason for that, if you look at these, so the mean residual air, when that's negative, that means that the projected demand from the model is higher than the observed values for water use. So these highly negative values mean that the model is over-predicting water use based on these calibration values from 2000 to 2009. And what's going on there, which I'll explain a little bit more about in the next slide, is that using data from 2000 to 2009, the calibration of the model ends up to predict water use, water demand to be higher than the actual water use, because people generally use more water in that time frame in their homes and have since then installed more efficient fixtures inside the home, as well as done various things, maybe xeriscaping or other ways to be more efficient with irrigation. And that's captured as some of the calibration parameters between those periods. But ultimately, take-home message there is that we really can't use the historical data going back too far to make a good estimate of current water demands and usage because of those changes in behaviors that we've seen over time. So this gets into that with a little bit more detail. And we have this is the list of parameters that are calibrated. So there's a default value for all of these parameters that's in IUWM in the interface model that you can use. However, of course, these can be refined to provide better estimates of water demand. So we have kind of two parameter sets looking at both indoor and outdoor demand. I talked about those alpha and beta values from the different residential end use studies and how those can impact water usage. And we can see, so if we look at on the far right here, we have the calibrated values from 2000 to 2009 and then 2010 to 2014. If you look at those, you see higher values, alpha values, showing that people generally during that time period had used more water than they did in the 2010 to 2014 period for indoor use for their fixtures. Same goes even with our commercial, industrial, and institutional demand. That has gone down on a per household basis since 2009. Then looking at our outdoor demand, we have a lot more parameters there that we have to calibrate to, and that gets to, you know, a lot more uncertainty really in those estimates of outdoor demand. We do pretty well at representing the trends, but on a month-to-month basis, it's not perfect in terms of estimates. So we have, if we just kind of look at a lot of these various parameters, like for example, precipitation response. So again, that's percentage of precipitation that people respond to. That parameter was about 25 in 2000 to 2009 calibration versus 69.2 people responding to precipitation events in 2010 to 2014. So, so there we see, and it's a lot of these parameters, we see that there's a pretty substantial change in those kinds of behaviors that people have with respect to irrigation. Okay, so we did calibrate the model to the entire water service area, but also we looked at a calibration on a per block group level. So here we wanted to see how well does the model, we know that it calibrates well at a municipal scale and can be applied well at that scale, but what if we want to calibrate a block or a block group and run some scenarios specific to that particular smaller area of a water service area? And so what we see here is Nash Sutcliffe values for total water use, and the values close to 1 are going to be where we have the best fit for observed versus simulated values from the model. Most of the areas were able to achieve a really good calibration. There's a couple areas in red that good calibration fit was not achieved. Actually, this one that's more north on the graph, or toward the top of the graph, that is Colorado State University. And one thing with that area is that it's actually irrigated with raw water that CSU has access to from a reservoir. So it does not make use of the municipal water. So that's a reason. So the model's based on the parameters, it's trying to estimate this outdoor demand, but then there's not an actual outdoor demand, outdoor water usage observed in that area because of that different practice. So there are ways that we could easily go in and adjust the model to be able to account for that. Also, this area on the south side of town, there's a lot of open space in that area. It's rather undeveloped, so it's not doing too good of a job there. Again, if we were to go in and really kind of change the parameters, we could represent those areas well also. Okay, so that kind of takes us now moving out of what we did in terms of calibration and verification of the model, and then now making use of the verified model parameters to actually run some scenarios of water conservation and reuse, as well as some scenarios of population growth and climate change. So this graph shows some different strategies for water conservation and reuse. And the indoor demands are shown in blue, and the outdoor demands are shown in green. So we have these various different scenarios. Our baseline is basically current conditions, and then we start to move into different scenarios of water conservation and reuse. So you can see with indoor conservation, the indoor demand, intuitively that goes down. Our outdoor demand stays about the same. We can achieve a lot of savings with irrigation conservation. That was a very aggressive scenario that considered adoption of xeriscape and highly efficient irrigation systems. So of course we can also have, we can get a lot of demand reduction, but then we move kind of toward these sort of hardscaping conditions that we often talk about in urban water systems. So between gray water, effluent, and stormwater use, those all worked out to be pretty similar. The scenarios run there allowed for the water to be used to meet non-potable demands like irrigation and toilet flushing. And then the roof runoff was pretty non-effective in our area. You really need a lot of storage in order to achieve adequate roof runoff, and that scenario really assumed people were installing systems with 55-gallon rain barrels, and therefore people could not achieve the same kind of savings that they could if they did larger scale stormwater harvesting and use program. Okay, so now starting to look at some of these scenarios of climate change and population growth. So here what we did is we have baseline condition again, which is the current, basically 2014 conditions in the city of Fort Collins. And then next to that, so for each month, we have the indoor and outdoor demand again. And then we move to a hot and dry scenario for each month. So the middle blue color and middle green color in each of these various months is our hot and dry scenario. So that was a projection of lower precipitation and a warmer climate, and assuming, I think it was a 10% increase in temperature to get these results. And you see here, of course, that doesn't impact indoor demand, but it does impact outdoor demand, and we get a higher projection of demand in the summer months from that climate change. We also ran a scenario of growth, population growth, and in that scenario, we actually looked at increasing the population, but in that, like I said, in that scenario, we evaluated really looking at conversion of low and medium density areas to higher density areas. So what happens there in each of these months, the far right bar is going to indicate that we have an increase in indoor demand resulting from the increased population. However, we actually see a decrease in outdoor demand because we're actually taking away irrigated area and replacing that with higher density development area. So that actually has a beneficial impact in terms of water use, but of course you have to consider what kind of impacts may be there from a stormwater perspective as well. So one other interesting application, I think, of IUWM is the ability to identify areas that deviate from typical water use. So a city may be interested in kind of identifying what areas are doing very well in terms of water use or using less water essentially, and what areas of the city maybe need some more assistance or guidance in terms of water conservation efforts. So what we did here was look at this from the block group scale again, and these indicate, these colors that you can see the scale for indicate mean residual air. So the negative values are in dark green. Again, those are going to be areas where the model overpredicts water use from the observed data. So what that means in this particular setting, so what we did is we applied a general set of parameters for the whole city, and then we looked at how each block group, how the observed data was for each block group in comparison to the observed values in comparison to model projected values using the citywide calibrated values. So therefore, these areas that have a negative mean residual air, or that are dark green, have higher water usage than other parts of the city. So their actual observed values are much higher than what the model projects using citywide values. And then the red areas are areas that use less water than would be expected based on those citywide calibration values. Okay, so here we can now say those red areas are doing really well. The dark green areas need some more help in terms of their water usage. So the city could then pinpoint some of those dark green areas or areas where they could target water conservation efforts and try to understand why the water usage is so high in those particular areas. Okay, so let's talk a little bit more about, I already provided some results on showing how urban growth and development, when you change from medium or low density into high density development, how that can impact water usage, and we saw that decrease in outdoor demand. but let's also look at kind of urban sprawl demand. So kind of building upon those results, seeing here we have all of these months of the year again, and our baseline conditions on the far left. And then the second column in each of these months is going to be high density development. So projection out to 2050 based on the population projections for the city of Fort Collins. Those represent the really movement towards a high density development, whereas the sprawl, which is on the far right in each month, indicates the water demand based on assuming that the water service area actually grows and open space is converted into medium and low density development areas, but that area is then added into the water the water area, so the water service area. So when we look at this, we can see that, so this can kind of give an idea of different patterns of development. So our baseline scenario, we have a certain indoor demand and commercial, industrial, and institutional demand that increases as we increase population to 2050. But then based on, and that's the same in the two scenarios, whether that development happens in high density or sprawl type of development, those indoor water uses stay the same between those two scenarios. But again, where we really see the difference is changing from the high density development, which is kind of infill, replacing the existing development, into sprawl development, where new land is acquired and developed, and that's added into the service area. That results in a pretty high increase in irrigation demand. So again, these are things that cities can use for their urban planning, but I'll repeat again, it's important to also consider stormwater and urban livability parameters, and that's things that we can be looking at through UN as these various scenarios are considered. Okay, so this just kind of takes that same graph that we just looked at and just kind of looks at a projection. This green line shows historical demand in the city of Fort Collins. And then we have a couple of different scenarios that are modeled there, including the sprawl in lighter blue with the X's, and then a sprawl with warming modeled above that in dark blue. So there we have sprawl development, and then sprawl development including adding in some warming conditions, which were projected based on some modeling that NASDAQ's group did here at CSU. And then we look at the model of density development and see how that ultimately changes the water demand over the years, from projecting out from 2010 into 2050 based on actual projections of population growth for those years. So kind of in order to start to summarize here, IUWM capability has been demonstrated to accurately project water demand and assess efficacy of water conservation and reuse strategies. We've also demonstrated its capacity to project water demand under varying climatic, population, and land use changes. And in summary, here in the city of Fort Collins, and I think you could kind of generalize that into our arid western region of the Front Range of Colorado, irrigation conservation can be really effective for water demand reduction. And we're learning about high density development and how that can impact water usage over future projections of population growth compared to other scenarios of urban sprawl. So with that, I can go ahead already and take questions.
Wonderful. Thank you, Sybil. So if you guys have any questions, feel free to enter them in the chat queue, and we'll get them relayed to Sybil. Alternatively, I could try to unmute you if you'd like to ask a question directly. So we'll give it a second, Sybil, see if anything
Sure.
Through. Well, maybe you blew everybody's minds and
Yeah, I doubt that.
they're left speechless. Harry is wondering, what are the climate scenarios included in the model?
Okay, so the model really has many different options for climate scenarios. So you can upload your own files, so you can do a climate downscaling for an area and upload a scenario of climate projections based on, and particularly a model uses, let me just actually go back to the slide where, since we have some time anyway, I think it would be useful to actually show this. Sorry, I just got to find where, all right, here's this. Okay, so the model makes use of PRISM data, but there's all sorts of climate data that can be downscaled for climate projections. So a user can upload those kinds of files into the system, and usually those have different scenarios that can be run that have different projections of climate moving into future years. So that's one way, is to just have those files load into the model and actually make use of those future weather data projections in a daily time step as the model runs to make those projections of water demand. The other alternative is to create your own scenarios of temperature offset by doing a percentage change, increase or decrease in temperature, and increase or decrease in precipitation. So for example, for the city of Fort Collins, we did some climate downscaling and figured out by the year 2050, I think they could project about a 10% or so increase in temperature, but that the precipitation wouldn't change very much. So the scenarios that I showed today just looked at those percentage changes in the precipitation and temperature, although there was not a lot of change with precipitation, like I said. So it really just modeled that temperature offset in terms of a percentage increase. So there's different ways you can create your own scenarios by just changing precipitation and temperature from the historical values by a certain percentage, or actually use PRISM or NAR projections of future weather data.
Great, thank you. Mary Santelman is wondering, so you confirmed that you're using the daily time step. Is there a capability of using hourly or sub-hourly time steps?
Okay. Yeah, so the way that IUWM is modeled currently is to work on a daily time step to include the functionality that it was designed for. It works well to do that. So really what we were looking at getting to here was running these different strategies of water conservation and reuse, and for those, a daily time step is adequate. So for example, if we're collecting even stormwater, we really just need to have an understanding of how much water was collected over a given day and can be stored. I'm going to go to my mass balance actually. So how much of that can be then stored into this source area, and then making use of that over time. Now, as we get more interested in trying to integrate the impacts of different stormwater strategies, and particularly green infrastructure, into how we think about urban water demands and water use and things of that sort, then there may be a need to run the model on a shorter time step, like hourly or by the minute. So that's something we're considering for future versions of the model, but at this time, the smallest time set that the model can run on is that daily time step, which is adequate for the type of information that the model currently provides.
Great. So Elizabeth Mack is wondering if it's feasible, sorry, this just moved on me, if it's feasible to integrate this platform with the data Matt Georgescu and Scott are generating, if you're familiar with their projects.
The data that who are doing, sorry?
Matt Georgescu and Scott Kranoff, they're on the 822 project.
Yes.
Looking at projecting future change.
Yeah, so I think that ultimately with UN, I think we have a lot of goals to really be looking at all of those future scenarios and to develop a consistent set of scenarios. So this certainly can interface with that. So as we talked about with these, all these various projections of particularly climate is something that's of interest with collaboration with those particular groups. We could make use of some of the projections that they have by uploading those files into our climate scenarios and running scenarios of IUWM, making use of those. So there's certainly the capacity to interface, and I think that one thing that we'll probably be really working to move toward within UN is to get everyone in the group working with a consistent set of data for future projections. And so I envision that moving forward there should be a lot more collaboration amongst our groups in order to do that.
Great. So Maria Wright is wondering if you've shared your modeling work with the local water provider, and if so, what type of feedback did they have on your projections and scenarios?
Sure. So we've actually collaborated with a lot of cities with this model, in particular the city of Fort Collins, who provided us with the data that we used for the verification of the model. We also have been collaborating with the city of San Francisco and Denver Water. And in particular, we've had the most interaction with the city of Fort Collins because, first of all, they provided us with the data set for collaboration and, for calibration. And that's a city that we have the most results from. They've been really impressed with the capabilities of IUWM. We've actually created a project through ERAMS that we share with them, and they can make use of the model to run some of their analyses. They felt like it does a really good job in comparison to what they have now, which is basically they project demands just simply based on a gallons per household water use value over an annual basis. So this really provides the city with the capacity to look at multiple different scenarios where they can say, okay, what if our indoor use changes on a gallon per household per day basis? What if climate changes, and provide a whole kind of range of possible future scenarios and water use for those scenarios, rather than kind of what they do right now is just spit out one value, and it's typically overly conservative for their planning purposes. So this can really provide them with the uncertainty and variability of what they could expect for their future water planning. So they think that it works well to represent the water use in the city, and then they really like how they can run these various scenarios. The same is true when we've been working with Denver Water, that they've been really impressed with how they could quickly develop all of these ranges of scenarios to kind of figure out where they could lie in terms of future water supply.
Great. Well, I haven't seen any other questions pop up, so that was a great discussion, and we will work on getting this webinar uploaded to YouTube and send that link out, and we'll be in touch with the Threats D and C information as soon as it's finalized. Thanks for your time today, Sybil, and thanks everyone for tuning in. You guys have a great afternoon.
Thank you, everyone.